All right, shall we guys start it? Yeah, so it's me again, Professor Mutlu, still out of town. And so first of all, I just want to go over some of the exam information that Professor Mutlu sent out on Piazza so that we make sure everyone is on the same page. So the first thing is, the most important thing is that the location of the exam won't be in this room, will be in CIC, the 4th floor of CIC. And there's a huge conference room called the Panther Hollow. So what you do is you enter the elevator, go up to 4th floor. Once you exit the elevator, make a sharp right, and you will see 2 pieces of glass doors. Just go into that glass doors and make a left. You will see the Panther Hollow room. So if you still have questions, send us emails. We'll try to give you some directions or maps on it. So this is very important. So make sure you don't come here on Friday. And the second piece of information is that the exam will be from 12:30 to 2:30. You have 2 hours to complete exams. And make sure you come early on Friday as well, ideally 12:25, because we're going to start sharp at 12:30. Okay, and make sure you leave 1 seat between you and your neighbor so that we can make sure everyone fits nicely. The next thing here is that you can bring a cheat sheet with you, a single letter size cheat sheet, double-sided. You can type it, you can write it, you can do whatever you want with it. And so everything that we've covered so far is a fair game until March 4th. So this includes everything, labs, homeworks, and even some of the required readings. So this exam will focus more on your analysis or critical thinking on how to solve the problem. So it will be less about memorization. So you don't have to force yourself to memorize all the terms. The most important part here is you should try to understand every single topic. So we won't test you on something that requires memorization. And all the sample exams are posted online from 2012 until last year. So you should definitely go through those because this year's questions will be similar, the style of the questions will be similar to the past years. So you should definitely go through those exams. And today is our review session on the midterm. So what we'll do today is Rachada and I will go through some sample questions from the homework this year and from the midterm last year. So after that, we'll take some questions from you guys. And if you guys don't have any more questions, then we'll probably end the class or the review session early. So let's go through our first practice question. Before that, does anyone have a, yes, you have a question?
Logistics questions.
Yes.
Are we allowed to get a calculator?
Oh, yes. So you're not allowed to bring a calculator.
And the extra credit parts which were included in the previous exam, is that like if you don't finish the first part of it, you can't attempt that, or you can just attempt it anytime you want?
You can attempt it if you want to. So one, yes, Kais.
Right, go ahead.
So I was going to say, if you're stuck on a question, try to move on because there are lots of questions in exams. You should pick the ones that you're most familiar with first. So don't just make sure you don't get stuck on a single question. Yeah, Kais.
So for questions, like for example, in a lot of the practice things for like LC3D ones, like the actual answer is like, answering less than 10 work, but then the point value is 4. So is there going to be space to like show work, make sure you get some partial credit, or is it all or nothing?
Yes, so as long as you are descriptive about what the LC3B design is doing, then we'll try to give you extra credits.
So, okay, so from what I saw in the practice exams, there's not like really space to like put your, to show your work other than like the scratch pads at the back. So there's only like the one little box to say like words are left.
So because the answers to those LC3B questions tend to be very concise. You can, if you really understand it, you can answer it probably within 3 words.
But then where do you show like state by like if, for example, shouldn't you get points if you can at least show like state by state what it does so you kind of understand what's going on? Maybe you can infer what it's doing. Like maybe that should be worth some points. Is there gonna be space to like show that work?
So I'm not sure about the grading policy on that last year. So Rachada, what was the policy on LC3B partial credits? Do we get credits if they somehow show some state transitions?
To some degree, if you know what if trying to do to some degree, then you get partial credit, but you get it correct. If you answer it correctly, that's the way you get it.
Yeah, so I guess
For states translation, I'll say the velocity last year was not much at best.
So it's kind of all or nothing.
Yeah, but it tends to be that way. But we're trying to give you as many partial credits as possible. Yeah. Okay. Anything else about logistics? Okay. So I'll go over 2 questions from the homework this year. The first one is out of order execution. So by this point, everyone should have done these questions, but it seems like some people still have some issues regarding this question. So I want to make sure everyone understands it well, because I guarantee you that there will be an out of order execution question in the exam. Okay. So here is an execution, out of order execution engine, or implemented something similar to Tomasulo's algorithm. And there are 3 major components here. You have the register alias table, RAT, and you have 2 reservation stations. And there are only 2 types of instructions here, either add or multiply. We also specify, let me see, what else do we specify? Yes, so in this question, we also specify how many instructions there are. If you look carefully, there are only 5 instructions that are executed: fetched, decoded, and executed. So the first part is try to list out all 5 instructions in the program order. OK, so how should we approach this question? And I'll try to briefly go over it. OK. Let's see. So what I usually like to do is I try to draw a data flow diagram of these 5 instructions, because that also gives you a high-level sense of orderings. And we know that there are 5 instructions total. And by looking at reservation stations, we can know which of those 5 they are. So if we first start with the multiply reservation station, we see that there are 3 instructions: x, y, and z. So let's find out what x is first. So x, if we draw a data flow graph, let's draw a multiply node. So what is x? So you can see that the reservation station entry of x has already been cleared. So that means it has already been written back to the register file. Then how do we find out what are the inputs and outputs of x? So this is something we can imply or infer from the other reservation stations. So for x, you can see that its destination tag is assigned to another instruction. In this case, is a, and add. So you can see that x is going to be forwarded to a, and it has an output value of 500. And next is we need to figure out the input registers to x. So for 500, we can see that you can see that in RAT, 500 corresponds to register R3. OK, so that's simple enough. So next part, I think the less clear part here is how do we find the inputs? So as we can see, x is a multiplication. So we can see that if we multiply register R1 and R7, you get 500. And they're both valid registers, both valid entries in the RATs. So we know that x is going to take R1 and R7. So now we have figured out x. So next node we want to take a look at is just take node y from reservation station, which is the following instruction after x. So it takes 2 inputs, 50 and 37, and you can find their corresponding registers as well. So 50 and 37, there are R1 and R2. OK. So now then we need to find the output register. which is y, with a tag of y. And we can see that in rat, with a tag of y, we see R4. So R4 is the output of y. Okay? So let's just move on to the next multiply instruction, which is z. So here, z takes the inputs from two previous instructions. And they are A and B respectively. So we can leave them out. So we don't know the register values yet, so we can leave them out as A and B. And it writes the value to a tag of z. And we're looking at rat that corresponds to R6. OK, so we're sort of done with the multiply instructions now. Let's take a look at addition. So we know add takes output from, take two inputs, one from x, one from y. So one from x, one from y. So that means the inputs are R3 and R4 respectively. Now we need to figure out the outputs. So the outputs is with the tag of A. And we, again, go back to the rat. We can find that A corresponds to R2. All right? And now we can sort of connect the outputs of A to Z, because the instruction Z takes in A's output, so which is R2. OK, so what's the next instruction, which is B? You can see that B here is an add with two inputs, 20 and 17. And let's find the corresponding registers in the rat. 20 and 17, they're R0 and R5. R0, R5. And again, it's going to broadcast its value to a tag of B. So now this comes to the tricky part. So how do we find out the output register value of B? Because obviously, if we look into rat, there's no tag B in here. So what we can sort of infer is that B has probably been overwritten. There's probably a write after write situation between two instructions. So we can, if we look at the rat, we see that there are three possible locations that B can write its results to. So the first one is R2. Then the next one is R4. The third one is R6. OK, so let's take a look at R2. Is it possible for B to write to R2? The answer is no, because A is writing to R2, which hasn't been fully committed yet, and A is an older instruction of B. So R2 is not a possible output for B. So how about R4? So R4, again, is not possible because Y also writes to R4, which hasn't been fully committed yet. And Y is an older instruction than A, and A is an older instruction than B. So this is not possible. So the final output or possible register value that B can write to is R6. So we can connect that to B. OK. So now we have our data flow graph. We need to determine the order of these instructions. So the first one is definitely X, because X has been committed. The next one will be Y right after X. The next thing we need to figure out is between A and B. So based on the reservation station, we know that the oldest instruction is at the top of the reservation station. So we know that after Y is A, then B, then Z, because Z is dependent on A and B. So Z has to come after A and B. So this will be instruction order. So does everything? Yes, print.
How did you logic over the fact that Y follows X? Because why couldn't it be X, A, Y?
So you have to look at the reservation station. So X has been, if you look at the entry, has been fully cleared. That means X has been written back already. But Y is still in the reservation station. That means it's probably still being executed or in the decode stage, because you allocate an entry in reservation stage and a decode stage. And Y, both of its tags, input tags, are valid. So that means Y is in the execution stage.
Okay.
Yeah. And we also, I think in the information on top, we also mentioned that the order's instructions at the top of your reservation station as well.
Okay, so it's because we see that both of the operands are valid, that we can conclude that it follows after X because it's in the execute stage, or it's finished stage?
Yes, so that's part of it. The most important part is X has been cleared. So this must be before Y, because X has been fully written back. It's either in the stage of write back or after write back.
Okay.
And Y is still executing. Yeah. Does everything make sense for the out of order question? Like, how do you determine the order of instructions? How do you find out inputs and outputs? OK. So the next question I want to go over is a caching question on, I think, homework 4 you guys have just done. Let's see. Enter full screen. OK, so this is a question I want to quickly go over so that we have a clear understanding of how to work on the cache problems. So the question here is figuring out different configurations of the cache. So associativity, block size, cache capacity, and the replacement policy. And we're giving you 4 sequences of instructions or address sequences. So we'll work on each sequence to figure out the different configurations we need. So sequence 1. So we can see that there's actually, let's put that. OK, that's good. So in sequence 1, we see that there are 6 addresses, 6 axes. That means there are 6 cache accesses. And the hit ratio here is 33%, which is 1 over 3. So what that means is, out of these 6 sequences, only 2 of them are hits. So 2 hits. And we have sequence 0, 2, 4, 8, 16, and 32. So we know that since we specified that the cache is empty to begin with, the first address is always going to be a miss. So 0 is a miss. Then next, after we access 0, it's a miss. We are fetching a new cache block from the memory and install it into the cache. So always the subsequent addresses that are in the cache block is supposed to be hit. So as we can see, so these addresses are pretty close in range. So if we need to find out 2 hits. So let's just say 2 and 4 are hits. That means 0, 2, 4, they're probably in the same cache block. But how about 8? So since we can only have 2 hits and 8 is a miss, we can see that the cache block is probably at a boundary right before 8, address 8. That means the cache block size is 8 bytes. From address 0 to 7. It covers address 0 to 7. So now we figure out the block size of the cache. OK, so next part is the sequence number, this long sequence here, and which has the same hit rate of 1/3. So let's take a look at how many addresses there are. 1, 2, 3, 4. OK, so there are 9 addresses. That means only 3 of them are hits. So let's take a look at how we can figure out some other information, either associativity, cache size, or replacement policies. So if we look at these address sequences, we can try to write out their addresses. So we know the bottom, I guess, bottom 3 bits are for cache. And now we need to sort of figure out the index bits. So here, there are 2 possibilities. Given that there are 2 possible, we give you 2 possible cache size. 256, that means it's 2 to the 8, and 512, 2 to the 9. So if we just, let's just say pick 2 to the 9, 512. So if we have cache capacity of 2 to the 9, the block offset 2 to the 3, that means the index is 2 to the 6. So you're probably, in this case, let's just assume it's direct map. So that means we're going to use 6 bits for figure out the index. So if you look at all these different addresses, we can see that. So 512 is 2 to the 9, 1024 is 2 to the 10, 1536 is 2 to the 10 plus 2 to the 9. All right? So if we use, just assume cache capacity 2 to the 9, that means their index bits are always guaranteed to be zeros. So all these addresses, they're always going to be accessing the same set of the cache. So even though they all access the same sets, we still get some number of hits. So I think we get 3 hits. So that means there's probably some associativity in the cache, so that even if we've had cache conflicts, we can still get some hits. So if you look at 0, address 0 is going to be a miss for sure. It's a code miss. So the next address is 512. Let's just assume we have some associativity. It's a hit. Sorry, it's a miss. So however, it's being installed in the cache. And 1024, it's a miss installed in cache. 1536 is a miss installed in cache. 2048, it's a miss. Let's just say installed in the cache. OK. So if we assume all these addresses, these 5 addresses, are able to be installed in the cache, that means the associativity is 5. And if we look at the next 4 addresses, which are repeated patterns, so that means there's some temporary locality. And if we assume we have associated with 5, we're going to get 4 hits, which is not the right number, because we're trying to get 3 hits. So what that means is we probably have that means one of the address is going to affix a previous address. So with an associativity of 4, we'll install 0, 512, 1024, 1536. And once we get 2048, it's going to affect one of the addresses here. OK? So if we assume that, that means out of the next 4 axes, we're only going to get 3 hits with associativity of 4. Does that make sense? OK. So that means, for this sequence, we figure out the associativity of 4. So the first sequence block size of 8. So let's take a look at the third one. OK. So the third one, we have a new sequence, 0, 64, 128. And again, the hit rate is 1/3. Let's see how many hits we have. So there are 9 addresses. That means we'll get 3 hits. So sequence 3. We get 3 hits. We know the block size 8 bytes. Associativity is 4. We'll look at the address sequence. Well, I'll just write it out. 128, 256. OK, so we have 2 possible cache size here, 256 byte and 512 bytes. So 256, 228, 229. OK. So we just pick a random cache size to begin with again. I'll just pick, I don't know, 229 maybe. So that means the bottom 3 bits are for the block offset, 0, 1, 2. And with the cache size of 512 bytes, we can figure out how many index bits we're going to use. So in this, since we figure out associativity is 4, we know that in total we have 7 bits. So 3 out of those 7 bits are used for the offsets. So there are 4 bits here. OK. OK, so if we assume, so if we take a look at address 64, that means it's going to be at set 0. And there are going to be all the same sets for the rest of the addresses. So they're all going to collide or incur conflicts in the same set, set 0. OK, so again, we have 3 hits. So the first one is going to be a miss. This is going to be a miss 2. 128 is miss. 256 is going to be a miss. And we have associativity of 4. So these 4 addresses are installed, along with their data, are installed in the cache. So 512 is going to be miss and affecting one of the addresses, right? Let's just randomly pick one. Let's say 256. So that means 256 is going to be a miss. It's going to be hit, 128 hit, and 64 hit and 0. So from this information, we can tell the cache size is going to be 512 bytes. And let's take a look at 256 to be sure our cache size is actually 512 bytes. So if we use 256 as our cache size, that means we're going to have 3 bits for our index. And bottom 3 are going to use at the offset. So if we only use 3 bits for the indices, that means 64, 226, 64, it's going to, so 64, sorry, yeah, so actually 512, what I said was wrong, because if we use 512 bytes, 264, 226 is going to have a 1-bit set in the index. So that means 64 is not going to be in the same set as the others. So that means we'll get more hits than 3 hits. It's only when we use the cache size of 256, then we can see that all of them fit within a single set. So sorry about that. So can you guys see what I've done here? So our cache size is actually 256. Because if we use 512, 64 is going to have a different set number. That means we're going to get more hits with that sequence. OK, so last sequence here is, so figure out the cache size, 256. And let's take a look at the last sequence here. So now the only missing piece of information we need is the replacement policy. OK, so here the hit rate changes to 1/4, a quarter. And let's take a look at how many addresses we have here. So if we have 8, that means we have 2 hits. OK. So if we look at these addresses, they're all going to be in the same set. Set 0, essentially. And 0 is going to be a miss. 512 is going to be another miss. 1024 is going to be another miss. Then we see 0 again. So it's going to be a hit because we have associativity of 4. So all these 3 addresses are installed in the cache along with their data. And then let's go to 1536. It's going to be a miss, and it's going to affect one of these addresses, 0, 512, or 1024. So if we just simply assume LRU, it's going to affect 512, right? Because we have recently accessed 0 already. So at the LRU stack, we have 512 being least recently used. So that just assumes LRU. Then we're going to get a hit on 0 again. And 2048 is going to be a miss. It's going to affect the least recently used. So in this case, will be 1024, and 512 is going to be a miss because it has been affected by 1536. So in total, we get 2 hits. So the policy here is LRU. And if we try FIFO, what will happen is when we access 1536, it's going to affect address 0 instead because it's a FIFO order. So we'll affect the first address, so which is 0. So that means it's not going to be a FIFO policy. It's basically LRU. Is there any other question related to this question? Yeah, Prin.
So would you recommend that if we have a caching problem, we should tackle it by finding the block size first and then the associativity, then the cache size, and then the policy?
I would say it depends on the nature of the question.
Okay.
So if it asks you about, for example, hit rate, miss rate, you definitely need to know those information. You need to figure out the block size, the index, how many bits are used for your index, and your associativity and capacity as well. So it really depends on the nature of the question. But the most important thing is you need to know which bits are being used as indices and which bits are using a block offset. Those can help you solve the questions. Yes, Selena.
Sequence 2, you assumed that the cache size was 512, but in sequence 3, you said it was 256.
Mm-hmm.
Would that affect the assumption in sequence 2, or doesn't?
I don't think it will affect it because if you look at the addresses, oh, did I just turn it off? Oh, okay, it's just my laptop. Yeah, so it's okay. I think we see on document count. So the answer is it doesn't matter because if we look at the addresses, it's 0, 512, 1024, 1536. If either the capacity of 256 or 512, they're always going to end up with a set 0, right? Because if the smallest address here is 250 is 512, so 512 is 2 to the 9, so the 9th bit is set here. But these bits, in this case, 512, these 4 bits are going to be 0, and in the case of 256, these 3 bits are going to be 0. So it doesn't matter which capacity you're using. They're always going to end up in the same set. Anything else regarding the cache question? Yeah, Ashish.
Have you grabbed the number of sets from the cache size? Just like the one there.
Okay. So you want to know how do I grab the set index?
The number of set bits.
Number of set bits, yeah. So basically, we know that, so from sequence 1, we know the block size is 8 bytes, right? So that means we have 3 bits being used for the block offset. So let's say 512 bytes. So it's 2 to the 9, right? So in total, you have 9 bits, but 3 bits being used as offset. So let's just assume a direct map. That means we have 6 bits here as the index, right? And that can help you figure out the set number.
Right. But because it's 4 ways associated,
You have to get rid of a couple more bits.
you have to get rid of 2 bits.
Yeah. So if in this case, associativity is 4, so you basically get rid of 2 bits to figure out the set number for sequence 3 and 4. OK? All right, so Rachada will go over 2 more questions with you guys, and then after that, we'll take some questions. So he's going to go over the questions from last year's midterm. So let's just enter full screen. Go single page. Which one you want to go over?
GPU.
Oh. Yeah. So here's if you want to work on this.
Can you guys see the document camera? Bill? Okay. So I'm gonna go over the GPU question first, and then the next question I'm gonna go over is a VM question. So this is also in the homework as well. This type of question, the GPU question. For part A, it's pretty obvious how to solve it, which is number of warps that are required to execute a GPU instruction if you break this C program down into a CUDA program. Usually it's just the number of iterations, which for this question is 32768 divided by the SIMD width. So in this case, it's 32 times 10 to the 24, that's 2 to the 15 divided by 2 to the 6. So that should be 2 to the 9. Does everyone get this part? Right? Okay. How about the next part? Now, given the same program over there, and here are the pattern of each content in array A, B, C, and D. The key here is if you want to figure out the utilization, you have to see on the branch statement over at instruction 1. What would make the condition such that when you're executing a warp, how each of the threads will go in terms of taken or not taken? And if you look at that branch, only A has any effects on the outcome of the branch. So you want to focus on the data pattern in A. And in this question, it said you have a repeated pattern between ones and zeros, and you have 29 ones followed by 96. I mean, you have 32 ones followed by 96 zeros, which means that when you're executing that loop, the first time it goes into the loop, you have 32 ones, 32 zeros. Or in the other where 32 of them will be not taken, and the other 32 will be taken, right? So the utilization of that particular GPU instruction is, so you have 32 taken, and then 32 not taken for the first 64 data arrays in array A. That means that when you are taken this branch, you execute 5 instructions, right? 5 instruction when taken. And then you have 1 instruction, which is just the branch when not taken. And if you look at the utilization in total, the maximally what you could get is every time you execute anything on the GPU execution units, all 5 of them will be executed. So that means that all 64 of them should be executing 5 instructions, which means 64 times 5. Here's the maximum utilization on the first 64 elements. But in reality, what you have is 32 times 5 plus 32 times 1. It's doing okay. Because the taken will execute 5 instructions, but the not taken only execute 1. So that's for the first 64 elements, right? So let me write it down here. So for the first. You have 32 multiplied by 5 plus 32 multiplied by 1 over 64 multiplied by 5. And that is 32 multiplied by 6, so that's 32 times 6 over 32 times 10. So that's 610. And then you have to take into account of the other remaining 64 elements, and it's all zeros. So that means that utilization becomes 100%. Do you get why that is the case? Right? Because when you execute that instruction, it goes on the same path on your branch. So that's why it's 100%. And so the total utilization of these programs, given that data pattern, is the average of 6, 10, and 1, which is 80%. All right. Yeah.
So if you instead had 64 ones and all of the threads were not taken, would you still have 100%?
Yes. Because if everything, when you are having a warp in GPU, so how it's organized is like this. You have a warp, right? And each one of them are just a bunch of threads. As long as it's going on the same path, each instruction within each thread will execute whatever the code is. So you have the full utilization on the GPU. But in this case, you don't have the 100% utilization because some of them are not taken, right? So during that execution, you have to mark those threads saying, I'm not going to execute this instruction for this thread because I'm not taking this branch. And then when it exits the branch and supposed to have the else statement over here, that the threads that are being marked earlier now become unmarked, and you execute those. And then you are masking the taken threads that took this branch. All right, so does everyone get how to, yeah?
So in this question, there are 64 CPUs, but what if the number of CPUs, and how does that actually work?
So let's suppose you have 32 wide SIMD. In this case, you see that, actually let me move this up. No. You see that the first 32 will fall into all the ones, right? And then the remaining 3 of the 32 wide will fall into all the zeros. So in that case, you have 100%. Say if you have something weird number like 30 wide SIMD, in this case, the first 30 will all be taken. Actually, it's not taken because it is not equal 0. So it will go on the same direction on the first 30. The next 30, you have 1, 1, right? And then a bunch of zeros, which means that you have the divergence of 2 of them will be diverging. The other 28 of them are not diverging, are diverging in the other direction in the branch. And you have to take into account the remaining zeros. So, and because this is unaligned, it's kind of hard to calculate, but you.
Overall SIMD utilization is the same.
It won't be the same, because in that case, you have, say, 30 wide SIMD. You have the first 30, right? It's all in the array A. All the values is 1. So it's going on the same direction. On the next 30 elements, you have 1 and 1, and the rest are all zeros, right? Which means that you have utilization of, so 2 of them are taken. No, actually, 28 of them are taken, so we have 28 times 5 plus 2 times 1 over 30 times 5. So that will be the utilization of the next 30, the next warp. For the next warp, everything is zeros, right? So now your utilization becomes 0. I mean, become 100%. So is 100%. And you have to keep doing this maths until it loop around to the repeated pattern. And because it's not aligned, it's kind of hard to calculate when that repeated pattern will happen.
So but if it's 32, 2 warps into loop around and it's preserve the same.
The reason why 32 is 100% is because it falls conveniently at the end of this one, right? So when you break each thread into the warp, it's every warp will go into one direction. Yeah. All right. So, any other questions?
It's just one.
Yeah, sure.
So if it's 128 centimeters, then utilization.
Then okay, if it's 128, let's see the data pattern. So you have 32 1 followed by 96 zeros, right? So you have 32 times 1 plus 96 times 5 or 128 times 5. And let's see if that's the same number. So that's 32 times 3 times 5. So this is 32 times 16. Yeah, so it's actually 80%. You see how I get that number? Right, so for the next set of questions, so I guess I already answered C. This is possible to get the utilization of 100. I mean, in this case, it's yes, because you can just make sure the data in A follow the same path on every time you break into warps. For question D, how many people said yes? You said yes, you said yes. Why?
Can I have 100%?
25. I mean, I already answered the first one. Right. So, what would be the data pattern for in this case?
I done the calculation comes up to
4 out of 32. So let's do the calculation given that we don't know that number. How do you actually try to do this calculation manually? Is suppose if 25% is 25, well, it's 1 over 4, right? So you have 1 over 4 equals, you have x number of threads going to one direction. So suppose you have x that are going to the taken direction, which you execute 5 instructions. And then you have 1 minus x that would execute 1 instruction. And in total, you have 64 number of threads, right? 64, and maximally you can do 5 instructions. And when you solve this equation, you get number of x. So let me do that calculation. So that's 16. So it's 80 equals 5x plus 1. Yes, yeah, it's 64 minus x. 64 minus x. So it's 16 equals 4x. So x becomes 4. You get how I got that number? All right, cool. How about the last question? Is it possible to get 20%? Anyone said yes? I work it out. Is it a yes or a no? It's a yes. So what if it's 20%? What's the value of x? All right, let's see what's the value of x when it becomes 20%, right? So it's 1/5 equals, well, yeah, x equals 0, right? So what would happen if x equals 0?
Get 100%.
Yes, so that's a no. Right. So do you guys get how this is why this a no? Because once every thread go to the same direction, it's 100% utilization. Right. do I move to the next page?
The virtual memory, right?
Yeah, but how do I move that thing? All right, have anyone actually tried to solve this question? Yeah, because actually we put this, something along the same line as this question on the homework last year. And after that homework, I got at least like 20 people coming to my office hour on how to solve it. And yeah, because we are evil, we put it in on the exam last year too. All right, so here's the question on VM. And I'll give you some time to work it out and think about this question a little bit. Let's see. And here are the two questions. It's actually easier to solve the second one first. So I'll give you a little bit of time to work through this. Also, in this question, pay attention to these two values for the hint, and also these two values. Like seeing what are the content of each entry, what are the content of the data in that the virtual address is pointing to, and what is the actual virtual address. Also, these two words. should I start going over this? Okay. So let's look at the first keywords. These two entries, as we said in the question, are the relevant location. So when you try to translate virtual address to physical address, what are the two things you need? What are the two things I wrote there that's not virtual address and physical address? So if you look at this, one of them is definitely has to be the physical address, right? Because we are storing that the content, the 0x0033733 into that virtual address. So one of these two has to be the I guess this has to be, one of them has to be physical address. And the only one left is the PTE, the page table entry. So one of that entry has to be the page table entry. The other one has to be the physical address. So what's the virtual address in this case for this question, for that pointer? Can anyone tell me what's the virtual address? Is there in the program? Yeah, it's the first line. It's 0xCCCCCC. CCC. Then, because one of these two is the physical address, which means how do you get the physical address from the virtual address? Right, so you first strip whatever is in the virtual address, break it into one of them would be the page offset, the other one would be the location of the PTE. Right, so what's the physical page number in this case? It's the location of the PPN. Yeah, so that's the physical address, yeah. So what would be the physical page number in this case? Yeah, because we both know that the PTE has to be one of those two locations, which means that the actual PPN is 337333. Do you guys get how do I got the physical page number? Okay.
Right now we don't know the size, so it might be 0 and 0 cc, some cc.
Right now we don't know.
We don't know the length of the physical page number.
Yeah.
Yeah, so it might be 0x0 cc, 7 cc, 0 and 0.
You mean 0 appending the? But if you know what is in the PTE, that data has to be a part of the PPN. Is that correct? And that's also in the definition over here. These 4 bullets.
Yeah, it's appending 0, but we don't know which bit it is starting.
Yeah, we don't know. So right now we know that this pattern, the 337333, will be a part of the PPN, right? Because then you append the page offset to the right, and then you get the actual physical address. So how do you get physical address? Well, actually, I haven't answered the previous question, which is how do you get PPN? How do you get PPN is, well, you know that one of these two entries would be the page table entry, which would point to the actual value of PPN, right? And both values are the same. So That's the value of PPN. Otherwise, you have to make a guess on which one would be the PPN. So you have to try 2 times and see which value would yield the PPN, the actual PPN. So do you get how do I got the number for PPN? No, okay. In general, without this question, how do you get PPN? VPN would tell you the location that I want to look for a VPN, right? So once you looked into that entry, and the location is one of these two data, chunk of data, and because both chunks of data are actually the same data, so I can make a deduction that, well, that's a PPN. So, well, the next thing we have to do is figure out what's the physical address. And that is PPN appended to the page offset, right? You append the two together. What can you tell about the physical address? What can you tell about the page offset in this case, given the virtual address? So one thing you can tell is this page offset, the last 4 bits, would translate to something like C, because your virtual address ends with the C, right? So it should be something like something, 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 and then C. And then you look at the location of these 2 blocks. It's either all C's or the C, D, C, 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 C. Then one thing you can do is, given that PPN is 3373333, you append these PPN with some amount of zeros from left and right, and then C at the end. Permute all the possible permutation that you can get. You definitely know how much the number of bits are needed to actually encode your actual PPN. If you look at the bit pattern in this case, you know that physical address is either C, 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 or C. Wait, what was it? That one? C, D, C, 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 C. You guys got that, right? So one of the 2 has to be a physical address that stores the actual content. Then this also equals to the PPN, which we know that a part of the PPN will contain.
We can't quite see what you wrote.
Huh?
We can see what
Okay. Right. So a part of that has to be PPN append by some amount of zeros. Because I mean, a part of that 33733 with some number of zeros with the page offset. You got that part? Yes, no? Because you know that the bit pattern that represents 3373333 has to be shifted left or right a little bit to get the physical address. And then you append the page offset toward the end to actually get the physical address.
I think it's easier if you write it in binary.
Yes. That also works. I can write that. So what's 337 That's 0, 0, 1, 1, 0, 0, 1. 7 would be 0, 1, 1, 1. Right, so that's 3, that's 3, that's 7, that's 3, that is 3, that is 3. And for some reason, it translates a bunch of C's, or a bunch of CC's, DCC. The only way that can happen, so you can shift this entire data to the left, and by actually, in this case, by 2 bits. And that would become 1100, 1100. Again. Right. Okay. 1101, and then 1100. And then the page offset. And if you look at the first few bytes, that translate to CDCC, which means that we got the content we want, which is physical address, because it's either CCDC or CCCC. And we know we have to shift the data, the 337 by 2 bits to append the page offset toward the end. Right, because if you look at the virtual address, it's a bunch of C's. If you break down a bunch of C's into binary, it's 1100. Right, so it's a bunch of these bit pattern. So you know this would be C, this would be C, this would be C, this would be C. And then to get the page offset, you have to cut it somewhere. Suppose you cut it here. Page offset becomes 0x, 0cc. If you cut it over here, it becomes 0x, 4cc. And you append the 337 to the left of these results to get the physical address. So what you have to figure out right now is where do we cut that? And the only place we can cut to get the physical address of either CCCCCC or CCDCCCC is here, where you have the page offset of 0011001100 or 0cc as a page offset, which is 10 bits. And when you have 10 bits in the page offset, the page size is 1024. It's 2 to the 10. Do you guys get how I got 2 to the 10? Because now you have the content of the PPN. You don't know how long the physical, the page offset is, but you know what the trailing data would be. It's just a bunch of C's. You don't know where you cut it, but once you cut it, you might have some leading zeros, and that will be appended to your PPN to get the physical address, and somehow that physical address become one of those 2 addresses, either all C's or CCD, CC, CC, CC. And you just try it out, and the only position you can cut is at the 10th position. That's why it's 2 to 10. Any question? I see puzzling faces. So you guys know how I got the PPN. Am I correct? You know, then you understand that PPN appended with the PO would be the physical address, right? The next thing you have to do is to figure out on that virtual address, where should you cut to get the PO? To get the resulting value becomes either all C's or CCD, a bunch of C's afterward. And the only place you can cut on your virtual address is at the 10th bit. That's why it's 2 to the 10 as the answer. All right, cool. So let's look at the next question. Yeah. So the next part of the question is, can you tell which one is the physical address and which one is the PTE? Given that given that setup and it executes without any exception. Also, afterward, what's the page table base address? Page table base address is the base address of the location of your entire page table. So which one is a page table entry over here? Is it CCD, CCCC, or is it CCCCCC? Is that rows of C's, right? Because you just did the calculation, then you figure out, oh, the page address, the physical address is CCD, CCCC, so you know that the other one has to be the page table entry. And also, if you can do it the other way too. If you attempt this question by trying to solve the first question before the second one, if you try to translate the virtual address to the physical address with that two possible value for the PTE, the CDCCCCCC, if you assume that's a PTE, you get you ended up with the physical address of the same physical address. You get CDCCCCC as a physical address, which would throw you an exception because now my physical address would point to the same location of page table entry, which should be like, well, how can that happen, right? So it throws exception. If you assume that CCCCCC is a page table entry, then you get CDCCCC with the physical address. Then you don't have the exception. And so you can tell that CCCCC is a page table entry. Then how can you get the base address of the page table? Any thoughts on it? How big? Yeah.
I guess subtract the virtual page number from the address of the page table entry.
Virtual page number.
Because what you access is the page table base
Yes.
address plus the
Yeah.
virtual page number.
Right. So you can subtract the virtual page number would be which indexes with just a bunch of C's into that.
Well, it would be a bunch of C's right shifted by 10.
Yeah, a bunch of C's right shifted by indexes 10, right? We should end up with 6 C's.
Wouldn't that be a bunch of 3s?
Is it 10? Actually, is it 10? The key here is actually shifted by 10 or some number? Because you have to look at the size. So what's the size of your page table? What's the size of one entry in the page table given that setup?
4 bytes.
Right, 4 bytes. So it's actually shifted by 8. because you have to take into account of the actual size of each entry. So instead of write shifted by 10 bits, now you write shifted by just 8 bits. So you write shift. Let me just use this page. You have C as the PT, right? And you know that PPN, I mean, the VPN is just some chunks in there. But to get the base address, you have to kind of like shift it back to the base and subtract it by subtract the PT by that number. But each entry is actually 4 bytes. So the number of bits you have to shift in order to get the actual value you want to subtract from the PT is this entire thing right shift by 10 minus log 2 of 4, because each entry is 4 bytes. So you right shift by 8 bits, which would result in 6 Cs. So you get that the page table base address becomes 0xCC minus 0x0, which is 0xCC, and a bunch of zeros afterward. Sorry about the misalignment. So do you guys get why it's not shifted by 10 bits, but 8 bits? Yes, no? Because you know that each entry is 4 bytes, right? If you shift by 10 bits, what can you infer about the size of the page table entry? The size of page table entry becomes 1 byte. 1 byte. Because if you look at the page physical address, so suppose this entire thing is a physical address, and here's the page table, right? Here's the page table base address, and here's the page table entry, which should be that a bunch of C's. And you know that those are the size of the accumulated entries up until 0xCCCCCC, right? Because over here in this block, it is just a bunch of, this would be page table entry. These also would be the page table entries, so on and so forth. So you have X number of page table entries, and each entry is 4 bytes, right? So if you shift everything before you subtract the value of the PTE, if you shift everything by 10 bytes, which is the actual page offset, then you miss the fact that each entry actually are 4 bytes, not 1 byte. So you have to shift by 10 minus log of the log of the size of the page table entry, which is 8 bits, to take into account of this 4 byte aligned entries. Do you guys get it, or okay? There's another question of the same flavor for this particular question. If you want to try it out, is for the extra credit on spring 2013 first midterm. And actually that question is a little bit harder than this, because you have to first figure out the base address, and then figure out where is your physical address such that it won't throw you exception. And they have different numbers, so you can try it out. If you don't understand how to solve it, you can drop by office hour, and we can kind of walk through it. But be aware that question is actually harder than this. Yeah. Or you don't understand this question in particular, you can drop by office hour. We'll explain it to you again. All right. Any other questions? Cool.
Basically, we'll just now take some questions from you guys regarding the midterm. Okay. I assume you guys are all ready without any questions. All right. So we can end now if you guys don't have any questions.
Can we ask like individually afterwards?
Sure. Yeah.